Welcome back, ladies and gentlemen. In this video, we are opening up a new chapter in conic sections, and specifically, we are going to be talking about parabolas and how they relate to conic sections. So you've previously watched the video that talks about how to, where do conic sections come from, right? And the generic kind of idea of conic sections is what happens when you split up a cone that is placed on top of another cone, right? That's really what it is. It looks something kind of like this, right? You get a parabola by making a slice that is parallel to the slant of the cone, and that ends up being the parabola. And that's exactly where we get that name parabola actually from, because it is parallel to that slant that you see there. And that's what we are going to be talking about today specifically, is the parabola, all right? Just the parabola. Now, we've talked about parabolas so many times in so many other math courses. You talk about parabolas, but you really kind of mainly focus on them in terms of their quadratic equations. And it's great, and it's a part of mathematics, but in this case here, we are going to talk about parabolas and their relationships to conic sections. And so we're going to step back, talk about a couple of terms that were referred to back in your Algebra 2 class, and then we're going to start diving on into a little bit more of how to pinpoint some of these terms and put it into conic form instead of quadratic form, like kind of that we are used to. So let's start off kind of first and foremost with just a little general idea of what we are talking about. So when we are thinking of a parabola, and keep in mind, this is true whether the parabola is going to be opening up, down, left, right, or even slanted, for that matter there. When you have yourself a parabola, what you actually have within the U of that parabola is a point. And this point we are going to call F, and that F is going to represent a term hopefully you have heard before, and that is the focus, all right? The focus is a point that lies on the axis of symmetry of the parabola, okay? It lies on the axis of symmetry of the parabola. And now that specific point F is a unique distance away from a second point, which would be the vertex. So I'm going to kind of assume right now that what I'm talking about is in terms of a parabola that's opening up. So that point F is on the axis of symmetry, all right? And it is a unique distance away from our vertex. Well, on the other side of the vertex, there is a unique line that is the exact same distance away from the vertex as the focus is. And so then ultimately what ends up creating the full parabola is the series of points that we can create from this kind of structure that I've designed here. And so really what ends up happening is that when you think about a parabola, there's a point that's a unique point here, that the distance from this point to the focus and the perpendicular to what we call the directrix, that is that line that's on the opposite side, are congruent to one another. They are equivalent to one another. And that would be true for all of the different points that you could create. So that line and that distance would be congruent. And then you can keep kind of going on up, right? If I did another one here, these would all end up being the same. And so then ultimately what we can kind of say is that's where these points from a parabola actually come from. And then the typical shape that we are used to seeing for our parabola there. And so that's actually what those points are. And the unique thing then what we kind of start to end up figuring out is each of these points end up having further characteristics in regards to the parabola. So that's what we're going to be kind of diving on into this lesson here. So let's take a look at a secondary diagram. So in this diagram, this is directly from your book. What I want to kind of look at here is the idea of this focus, the directrix, and the vertex. So as you can see, here's our focus. As I told you before, it is on the axis of symmetry. This guy here is our vertex. And then there is a unique length from the vertex to F, right? There is a unique length from that vertex to the value, or the ordered pair of where F is. And that's denoted usually with a length of a lowercase p. And then the truth would be then the distance from the directrix to the vertex would also have the same length. Now, I'm showing you this, and most textbooks will show you this on a slanted parabola, just so they can kind of universally use P. But when we're thinking of this in terms of a parabola that's going up versus one down, well, that's when it changes whether or not P is going to be positive or negative. And similarly, when it's going opening left or right, that also changes whether P is going to be negative or positive. And so, but usually we want to kind of show you first and foremost on a slanted parabola, just so we can kind of say universally this is what P represents here, okay? So as we can kind of continue to go on, what we're going to start to realize is that, well, from F, okay, it's a certain distance away to the vertex, but what about a certain distance away from the parabolic points in general? And so if you were to make a line that is perpendicular to the axis of symmetry, so perpendicular to the axis of symmetry, what would be true is that the distance from F to these 2 points that I'm highlighting right here are actually equidistant to one another from that value of F. And specifically, it has a value of 2 times P and 2 times P. And so the entire distance from point to point would actually be a distance of 4P all the way across. But again, that only works if it goes through the focus, all right? Only if it goes through the focus, all right? So what we call these guys right here is P is really always known as the focal length. And then we think of the distance from here to here across the focus. That actually is an absolute value of 4P, and we call that guy the focal width. And of course, we're using absolute value because length is always going to be positive in that aspect there. So these are some kind of things that we need to really understand. And when we think about this in general, let's go ahead and take this information and actually define what a parabola is. All right, a parabola, simply put, is the set of all the points that are in a plane that are equidistant from a particular line, that's our directrix, and a particular point, and that is our focus there. And so that's ultimately what a parabola is. It's all of the points that are equidistant from the directrix and to the focus. So how does this kind of help us out? Well, what we're going to utilize this information for is to kind of think about what are all of the different forms that we could write it in. So let's think about what happens when we have a parabola opening up or opening down. Well, we write this in conic form as x minus h quantity squared equals 4 times p times the quantity of y minus k. So this is when it's opening up or down, and then p would be positive or negative depending on if it's up or down. And so where h and k in this case, h and k are the vertex. So h comma k is the vertex of the parabola. Well, if we're going to open left or right, so if I'm going to open left or if I'm going to open right, Well, then the only thing that really changes is what's going to end up being squared. The x's aren't squared anymore because now it's going to be kind of, if it was on the origin, right, you would end up kind of having the axis of symmetry on the x-axis. And so now, instead, our y values are going to end up being squared, and our x value is going to end up being the unsquared term multiplying by 4p. And again, opening right, if you're going to have a positive p, and then opening left, you'll end up having that negative p that you have there. Okay? So let's take a look here at a couple examples that kind of just put some light into what we're looking at. It says, find the focus and the directrix and the focal width of the parabola. So if you see here, we have a parabola that does have a squared x term. It has a squared x term. So that means we are going to be looking at a typical up-down parabola, but you also don't see an h or a k. You don't see anything inside of our typical our typical parentheses of an h and a k. And so let's think about what we're looking at here. So if we go ahead and take a look at this in terms of our x squared term, I want to go ahead and put it into conic form, and I'm just going to multiply both sides of our equation by a -3. And the reason why is because I want to put it into that conic form that we had before, where we had the p being multiplied by the unsquared term, okay? So just that kind of helps us put some things into perspective. All right, so from that point, we now see that the coefficient of the y is going to be equal to -3. But really, this is the 4p in the little formula that I was showing you guys before. So 4p equals -3. And so really what we see is that p has a value of -3/4. And so since our vertex was going to be at 0, 0 at the origin, because I don't have an h and a k, so then what I can do is that I know this guy here is going to have a focus at 0 and then -3/4, right? So our focus, I'm going to call it F for focus, is going to be at 0, -3/4. Okay, so that's going to be where our P is. So let's kind of draw this out and see what we're looking at. So there's our vertex. And since that is a negative P, it's going to open down. And so I'm going to be right here at F at -0, -3/4. Okay, it also wanted to know what the directrix was. So the directrix is now just going to go up 3/4, okay? So I'm going to go up 3/4. Now, this is real simple when the origin is the vertex. It's just going to be on the opposite side. So it's going to be right here at the line of y equals 3/4. So this guy here is our directrix. And then last but not least, to find the focal width, well, the focal width is going to be that 4p. So the focal width is going to be the absolute value of 4 times p, which is -3/4. So the 4's will cancel, so the focal width will be 3. So these were the 3 pieces that we needed to answer this first example